this. So, hi everybody. My name is Marta Gonzalez, and first thing first, I want to thank the organizers for giving us all the chance to meet physically, and also for giving me the chance to share my work. Second important thing before starting, I haven't done this work by myself. This is also the work by Néstor Sánchez, Emilio Alfaro, Manuel Jiménez, and Mari Carmen Sánchez Gil. And it's a little part of a paper led by Emilio there. And well, what I hope to do in the few minutes that I have here is to pique your curiosity a little bit. So you look forward to the paper, and maybe if we have some time, you ask some questions. Okay, so I'm going to talk about the spatial structure of young galactic clusters. So let's start. So for context, a couple of things you already know. Star formation is a complex process, specifically clustered star formation, which starts from the collapse of a huge molecular cloud, and it involves a lot of physical processes. But we do know that, or we have observed, or we have evidence that it is hierarchically distributed spatially. And not only here, but also I take the chance to show you this beautiful image of NGC, I think it's 1566, but I cannot see it, where you can see the different structures as ellipses embedded within one another. This picture also highlights that this hierarchical star formation that I was talking about also happens within a context, within a galactic context, and the galaxy itself has some structure that is also complex and we should also consider. So I am really excited about the future after all that has been said here about Gaia data releases, but I'm also quite happy with what has already been shown to the community. And let's say, paraphrasing, that this work I'm going to show already stands on the shoulders of a lot of people that made possible the dataset, so the Gaia collaboration. But in this case, it's also based on the work of additional people, because we don't use the data releases directly. We use a sample of young open clusters. So we use a subset of the clusters detected by Cantat Godin and Tariq. So, but we have selected the youngest and within the extended neighborhood from the sun. This is the sample in the galactic plane and with the height in colors. So what we are going to do is to try to obtain the hierarchy of these clusters and use them to sample the small to intermediate scales between hundreds to a few thousands of parsecs. Okay. Now, the first indicator of these kinds of phenomena, and the roughest one, would be a fractal dimension. And this is generally estimated from a correlation dimension, which comes as the linear fit of the correlation integral based on the distribution of points, clusters in this case. And we have obtained values, this fit for the reliable values, which are marked here as black squares, which are consistent with turbulence-driven hierarchical star formation. Now, this motivates us to try to extract this hierarchy of clusters. And I won't get into the method, but we use optics, which is not really a clustering method, but a reordering algorithm. And its products are not, its direct product is a plot like this one, a reachability plot, where the densest parts are seen as valleys. So we kind of see all the all the hierarchical structure here in terms of there are valleys and dens within the valleys. And that's what is used to detect clusters in this case. So this is the reachability plot associated to the sample that I just shown you in the previous slide. And these are the results. So you can see we have 15 groupings, structures in total, and clearly nested within each other. Now we separate them by hierarchical level recursively. So groupings of level 0 wouldn't contain any other clusters or groupings inside, like these 3, okay, in quadrants 2 and 3 of the distribution. Level 1 would contain some level 0 inside, like B, E, or F. Level 2 contain level 1. In this case, we only have one, coincidentally, where we are right now. It would be the local structure here. And finally, we have a level 3 class grouping of almost all the stars in the sample, all the clusters, sorry, in the sample, except for this lonely guy here. Well, first of all, I highlight that the most complex stuff is happening right here in the solar neighborhood. And well, it's not the first time, since clusters have very good determinations of their physical parameters, that finding clumps of them has been tried. And here's a comparison with the complexes and supercomplexes from Efremov and Sidnick in the 88, with, of course, much lower quality data. But the resemblance, they found complexes and supercomplexes with open clusters and associations, and the resemblance is striking. Also, the sizes of the structures we obtain correspond to their complexes and supercomplexes. And focusing a little bit on the central structure, our local structure, it's not only the most complex, but also the better populated within the sample. And it would be consistent with star forming supercomplex associated with a segment of the spiral arm, possibly due to shear, but its specific origin can still be truly discussed. Now, what the structure we obtain, which is here in the small square there, can be compared with some results from other tracers, but these are different data sets. So there are differences between what we analyze and what they have done. And ours is the, so on the left, you have the groupings, which are, let's say, clusters and associations, the young ones from Kunkel and collaborators. And then the two on the right are based on stars. The one in the middle shows the overdensity of young upper main sequence stars, and the one on the right shows a sample of OB stars by Pantaleon y Gonzalez. And the structure we find is mainly on the overdensity of all these other tracers, but there's, of course, some difference that when we have more time, or maybe if I finish early, we can discuss with a bit more detail. And now, the last thing I want to talk about, but just a little bit, is that some analysis using the subsample of which we have the complete 6D phase space information seems to show that the structure we find, and particularly that of level 1 and higher level, is coherent, kinematically coherent, because it appears also when we perform the clustering in 6 dimensions. And the picture, as you can see, is somehow the same globally. The most complex structure is still structure A. The whole sample seems clustered, and I think this is the main things that I wanted to say. So I leave you with the summary and conclusions there, and I will answer questions if we can.
Perfect timing, not even the 4-minute warning. Thank you. Okay, great. Thank you very much, Marta. Is there any questions in the audience?
I will make a question. And we have been detecting clusters with Alfred, Castaginar, and Cantangoden. We have always the dilemma of saying what is a cluster actually. Because all the clusters that we have detected are biased by minimum number of members that we have set. And also because now, even if, well, especially in the very young clusters, we have found a lot of substructures. So if you decide that these two substructures are only one or not, or we decide, well, we can label that as two clusters or just only one, I'm wondering how this may affect the results.
What we would find, well, actually, my speciality is lower scales, much smaller scales. And in that case, I can comment that I think that the small scale, that the minimum number of members is a very important constraint that I think that for now we should keep, particularly with huge data sets like we have now, because random fluctuations, otherwise, what you get is a lot of spurious detection associated to random fluctuations in stellar densities. In this work, if you consider two subclusters as one, what we would get is two very close points. However, we also still apply, because optics is, let's say loosely, that it's an extension of DB-scan, but it doesn't throw away the minimum number of points requirement. It extends only on the scale. So it's a bit, it probes lower densities, but by opening the radius, not by taking less stars. So yes, but the method is the same. I mean, in the end, there are points for me. So what I would have, if you decide that the case you proposed, I would have two very close points, just simply. But just two very close points wouldn't make one of these either. Yes, that would be, it would probably, now that you say it, you would well, actually, it's...
So I don't know.
No, fractal dimension is very robust. It's kind of, even we have exactly the same exercise with another kind of data. For example, for Hamper, the same, and also for Diaz catalog, the last catalog, and the situation is completely similar in the case of the fractal dimension.
But for fractal dimension, what you have to be is a bit strict on the scales. You set it, you know, because I mean, the slope can change and should change. It is expected to change associated to other processes.
Can I say? Yes. So the interesting question here is that in comparison with the remote data, maybe with Lingo data, the 82 was a compilation of different distance of ages, nothing to do with Gaia and something like that. The results are very robust, and it is because the these studies, if you are using a very good sample of data, in the case of the number is good enough, the results are very similar to each other. So I was astonished with this data when, for the first time, Sophia Randish with the guest data and Gaia, the first Gaia review, I don't remember the name, was made with Marcos. So the distance and the age was very, very similar within the error that's obtained by, the classical.
Yeah. What Gaia have changed quite a lot is so we have rejected a lot of clusters that were not clusters actually, that were just asterism, and we have added a lot. But it's true that the ones that have been confirmed as clusters have, the distance have not changed much, and that's
You have right that, for example, the definition of the cluster radius is a problem here, because what is the border of that? How do you define that? No? So,
and when you take the young ones, which are irregular, it's true.
What's true that in our search for new clusters, we have been very conservative and we have tried to minimize the false positives. But there are other works using DB-scan or HB scan that have been less strict than us. And there is a lot of new clusters that are not included, neither in Cantan, not in Toric.
We know.
That may be clusters. And then we have many more points there. I don't know how this changes.
In the end, when you select a sample to do an analysis, you always have to choose between reliability and contamination, So we actually chose this one because it was more conservative, and we were sure that more certain that they were where we wanted them to be.
Fascinating. DR3, Gaia
So look
3,
forward for the
will
paper.
help for sure in this problem. So let's thank our speaker again.